Thank you for the introduction. Hi everyone, my name is Doug, and now I'm going to talk to you about how we support Android developers in writing secure code. And the problem that we want to tackle in this work is there are many mobile applications with poorly implemented privacy and security mechanisms. In particular, we focus on Android applications. And researchers have shown that developers often make mistakes in choosing a secure option for their network connections. And furthermore, they also sometimes or oftentimes misuse cryptographic APIs. And just yesterday, there was a talk here talking about how developers expose users' private information to malicious third-party applications. So we need support for developers. And speaking of supporting developers, Google has taken a step on this work, and they integrated Antralin, which is a scanning tool that performs code scanning to improve the code written by developers. And one aspect of this is the security. And this is an example of how Antralin helps you or helps developers in writing code. But this is before the support of Antralin. So in this example, we have an insecure hostname verifier where developers simply returns true for the function verify, and this is insecure because it accepts all hostname, doesn't verify the hostname at all. And this is the result with the support of Antralin. Now the question is, do you see the difference? So the difference here is this highlighted code. So the method is insecure, and Antralin tries to notify developers by highlighting this method name. The problem is this way of notifying is barely visible to developers. Let's take another look at this example. So let's assume that developers actually pay attention to this insecure code. And they move the mouse over the highlighted code, and they see a corresponding warning message explaining what the problem is and how to fix it. This is the second example. So instead of returning true, we put a Boolean variable that has the value of true, and we return to that variable. Let's say this variable is testing. We are testing our application, and in this case, Antralin fails to detect this vulnerability. So we have two examples, even though they are very similar, but Antralin fails to detect the second case. And the third problem is, let's say if you are a developer, you are notified by this mistake, but you don't have security knowledge. How do you fix it? So in this aspect, Antralin doesn't provide quick fix or doesn't provide help in terms of quick fix. So to sum up, we have found three problems of Antralin. The first one is the usability aspect, because the way you notify developers may not get full attention from developers. And secondly, due to incomplete static analysis, you may miss some trivial case. So in this example, these are very trivial, but for the second case, Antralin misses. And lastly, it doesn't provide help in terms of quick fix, meaning that for developers who are aware of the problem, but if they don't have security knowledge, they don't know how to fix it, or it's very hard to fix it without security knowledge. And with that in mind, we have developed Fixroid. Fixroid is an Android stereo plugin that identifies prevalent Android security best practice, and it tries to offer more secure solutions instead. And this is the architecture of Fixroid. So we have inspector that reads from the config file which security resolver is available. So whenever developers write code on the code editor, inspector will ask security resolver if a given code snippet is insecure or not. And coming back to the inspector here, we apply or we use the static analysis of IntelliJ, and we perform static analysis on 4 different levels: package level, project level, class level, and method level. This will help us to eliminate mistakes that Antoine makes. And when inspector got the answer from security resolver, it will forward that information to telemetric manager. And together with web service and database, these three components are responsible for the infrastructure of our final study. And it also helps us to learn how Fixroy interacts with developers, or how developers interact with Fixroy, so we can improve Fixroy over time. And at the same time, inspector will also forward the information regarding the insecure code snippet to line marker. So line marker will notify developers by a usable security indicator. Inspector will also use the same technique that Antoine uses to notify developers. So here, Fixroy has two channels to notify developers. One is the same technique that Antoine uses, and the second one is the security indicator with the line marker that mark those lines of code to be insecure. And this is an example. These are two examples of how Fixroy works in real-world situations. So in the first example, we have an insecure network connection. So in the first example, we have an insecure network connection where developers simply use the HTTP protocol for their network connection, while the HTTPS is actually available. And this is insecure because data is transmitted in plain text, and this is vulnerable to the man-in-the-middle attack. And Fixroy detects this. It highlights the insecure code and provides the security indicator on the left side beside the line number. And similarly, for the second example, we have SQL injection vulnerability where developers concatenate the query, the SQL query, with users' input. And this is vulnerable to SQL injection attack, where attackers can inject SQL command to the query string. And when Fixroy can provide a quick fix, developers can simply enable the quick fix by using the default shortcut of Android Stereo, or by clicking on the security indicator on the left side in the previous slide. So we have talked about telemetric components. Our goals here are, we want to improve Fixroy over time. And secondly, we want to measure if developers have learned writing secure code over time with the support of Fixroy. So we want to measure if Fixroy has helped developers in writing secure code in a long-term study. And finally, we want to conduct an ecological valid developer studies remotely. So meaning that we don't want to invite participants into our lab, stay there and observe them do the programming task. We want to do that remotely, online. So with that in mind, we want to record first the security bad practice and security good practice. But we don't record raw information. Those good and bad practice info has been hashed before sending to our server. So we know that there's certain problem, but we don't know exactly where the problem is located, and we don't even know who the developer is. So when Fixroy detects a security problem, it notifies developers, and for that reason, it wants to know if it gets developers' attention. So when developers pay attention, they read the warning message, and for that reason, Fixroy also records if developers read the warning message. And similarly, for the quick fix, when Fixroy provides a more secure solution to a given security vulnerability, it also detects if the quick fix is applied by developers. And finally, to learn developers' experience while they are interacting with Fixroy, we ask them some questions. We call this experience sampling. So now the key question is which security pitfalls FixRoid covers. We extracted from the existing research and from the Android official documentation. And in particular, our list includes first the insecure network connection, which is extracted from the Malo-Troy paper, where developers may use the insecure options such as the HTTP protocol, like in the previous example that I have shown you, and can be that developers implement the hostname verifier improperly. We also extract some common pitfalls in terms of cryptographic APIs misuse from the CryptoLink paper. Furthermore, we check or FixRoid checks if developers write code that is vulnerable to SQL injection attack, and if developers use a web view object that loads a local HTML file from a publicly accessible folder while he enables the JavaScript execution, this is also checked by FixRoid. And similarly, when developers try to load code dynamically, but through the insecure channels, such as the HTTP protocol, or he loads code from publicly accessible folder, FixRoid also try to detect this. And lastly, if developers store user private information on publicly accessible folders, such as the download folders, but he stores user email, phone numbers, or password, this is also checked by FixRoid. So we want to see the very first insights on how FixRoid interacts with developers. Therefore, we conducted a pilot study, a remote pilot study, because we want to know how they perceive the FixRoid when they are writing the code. We have 3 programming tasks: string encryption. We want to know if developers are aware of, or if developers are knowledgeable in using cryptographic APIs in Android applications. And for this task, we provide them, for every task, we provide them code skeleton and test case. So in this task, we give them a string and we ask them to encrypt this string. And for network connection task, we give them a domain and we didn't give them a protocol, so we ask them to connect to this domain and give us the status code, the return status code. And for SQL query, we attached a SQLite database into the code skeleton, and we insert several records, and we ask participants or developers to query a given record from the database, but with a variable username. So the username here is supposed to be user input. We want to know if developers are aware of SQL injection attack. So we have recruited 9 participants. They are our industry contact, and all of them are experienced software developers, while 5 of them are Android developers. So after they finished the study, 2 researchers sit and manually examined their solutions. And if they cannot come on a final agreement, then the 3rd researcher will join to solve it. And this is the result. So we have data from the exit survey, and we have data from telemetric components. And when they finish the programming tasks, we asked them we invited them to join in our exit survey to ask them some questions. And now, when they are asked about security indicator, they reported that, all of them reported that they noticed this security indicator when they write insecure code. But for the highlighted technique that Antralin uses to notify developers, only 2/3 of the participants notice that there's something wrong with their code through the highlighted technique. And with the telemetric data, we see that 2/3 of the participants used the provided quick fix by FixRoid, meaning that FixRoid has helped 2/3 of the participants write secure code, one more secure code. So with that in mind, we decided to conduct our final user study. So we want to draw the line between one group without FixRoid activated or with only telemetric features, and the other group with the full support of Fixroid. So we want to see if Fixroid creates some difference in terms of code security. We have the same 3 programming tasks, and the question we want to answer here is, does Fixroid have impact on code security? And this is how the study goes. So first, we send invitation email explaining about the study. They are provided option to not joining in the study, just using Fixroid, or they are also provided the option to stop receiving email from us in the futures. Once they decided to download, install Fixroid, we show them an instruction about the study that we provide them code skeleton for every single task, and test cases are provided so they can run to check if their solution actually works or not. And if they find uncomfortable solving a given task, they can skip it, or they just don't want to solve it or not able to solve it, they can skip it. And if they decide to just skip the study, they can keep using Fixroid. Once they join the study, they can solve tasks one after the others, and the orders are randomized by our web service. And when they interact with the certain components of Fixroid, we ask them some questions. For example, if they use a given quick fix, we ask them, do you think this quick fix is useful or not? And once they finish the programming tasks, we invited them to join in our exit survey. And in this exit survey, we ask them several questions in general. And then for the group with Fixroid fully activated, we ask them some specific questions. And finally, we ask both groups demographic questions to learn more about them. So we tried to recruit developers with Android experience. So our target was Google Play developers. And for that, we have crawled email addresses from Google Play Store. We tried to reach out to them, but this is a time-consuming study, and we couldn't reimburse them for the study, for the participation. In the end, we got 16 valid participants. So in aiming for a higher number of participants, we tried to recruit students. But we only want to have students with Android programming knowledge. Therefore, we ask them questions before inviting them into to participate in our study. So in the end, we have sent 59 emails, and we got 23 valid participants. We give them, or we reimburse them 25 euros as compensation for the participation. So in total, we have 39 valid participants who have written code and who have filled out our exit survey. And this is the demographic data. So we have 2 participants reported that they don't have solid Android programming experience, but these are also the ones who have taken Android-related programming course, and the rest are experienced Android developers. Regarding the country of origins, we have developers from almost all over the world, while we only invited students from Germany. So similar to the pilot study, once participants finish finish the study, researchers sit and manually examine if a given solution is insecure or not. We first look at the functional correctness of their solutions. So here, we don't really see significant difference between these 2 groups, the one with fully activated Fixroid and the other one without Fixroid. And in both groups, anti-aliasing is enabled. However, when we look at the security correctness, we see difference here. Especially in the encryption and connection task, the difference is significant, and with the exception of SQL-like SQL query task. So we apply statistics to evaluate if the difference is significant in total among these tasks and among participants. So we use logistic regression because we only care about the binary outcome, whether a given code or given solution is insecure or not. And our null hypothesis is fixed right does not have impact on code security, or fixed right does not improve security. And after the analysis, we got the p-value of 0.005, meaning that we can reject the null hypothesis, and we can say that fixed right does have impact on code security. Regarding the telemetric data, when participants use the provided quick fix by Fixroid, we ask them, do you agree with the following statement? The provided quick fix was useful, and the majority of both students and developers agree or strongly agree with the statements. So for our future work, for the user study, we want to be able to compensate developers because we want to have more participants who are Google Play Store developers. And we also want to cover more sophisticated security pitfalls because in the scope of this work, we only focus on what existing research have found regarding popular Android security pitfalls and also from the Android security best practice. And lastly, we want to learn from the open source. So if we have new security pitfalls, we need to update fixed source code. But if we can learn, we can use machine learning to learn from the open source community. So if their security changes from insecure to be more secure, we can learn that and integrate into Fixroid without having to update the source code. So to conclude my talk, previous work have shown that developers' education is not enough. We need tool support. And current generation of tool support is suffering from usability issues. So in this work, we presented Fixroid. It enhanced the static analysis of Android lint by performing static analysis on 4 different levels, project, package, method, and class levels. And it improved the usability of how developers should be notified about a given security problem. And lastly, not only detecting the problem, but Fixroid also proposed possible more secure options instead. So we call it quick fixes. And we validate our approach with an ecological valid developer study. And we did that with 39 participants. They are either students or developers with Android programming experience. So and the result confirmed that Fixroid significantly improved code security. So with that, I thank you for your attention, and this is a summary slide about what I have been talking so far. Thank you very much for your attention.
Thanks for your presentation, Abhik Roy Chaudhary from NUS. I just have a very quick clarification. Most of the fixes that you provided, they seemed really simple. So instead of conducting such a user study, wouldn't it be more natural to treat them just as auto fixes? That means whenever these patterns are detected, the tool just employs these fixes. Why do this user study? Because it's also borne out by the results that they found this useful, and it's not surprising.
Yes. So thank you for the question. And so we try to pick these tasks with regard to the popular security mistakes in Android applications.
Mm-hmm.
So we pick these 3 tasks because for the network connection, it's very popular that developers, if they don't pay attention to security, they simply use the insecure option, which is the HTTP protocol. And similarly for the other 2 tasks.
But would it be fair to say that the quick fixes you are providing, they could very easily be just integrated as auto patching rather than having the developer validate them?
Sorry, what do you mean by auto?
That means the tool just employs these transformations even without the developer being aware of it.
That is very good point. But in this study, we didn't look at that. But thank you.
Yeah.
Hi, Daphne Yao from Virginia Tech. I really love the work. I personally also done some related work. I have one thought and one suggestion. The thought is that a lot of the secure code, for example, you mentioned cryptolint. It will help if you talk a little bit about the specific crypto vulnerabilities, and because security is always respect to particular type of properties.
Yes.
The suggestion is related, which is I think it's probably not very surprising that your solution helps. Probably a related sort of a harder problem to evaluate is to what extent it helps in the sense that security, there's it's secure, but then what specific properties of a secure the code is secure? For example, are there any aspect of security you fixed Droid does not cover, and then the programmer thought it has covered, and therefore by running your tool, and they will say, oh, I'm running the tool, I don't have to worry about the security, I'll just and so the scope of the guarantee probably need to be evaluated, and then just see whether the users have any sense of that. And just a suggestion.
Yeah, thank you. That's very nice suggestion, because I think we need to have context as well about a given task. Yeah, thank you. Yeah, yes, please.
Hi, John Criswell, University of Rochester. So, one question I have is, so as I understand, developers wrote code, and then the tool found security problems and then suggested fixes, correct? That's the way the study worked?
For the group with fully activated Fixoid.
Okay.
Yeah.
So, for the developers, did you ask them to write secure code, or did you just ask them to write code? Because depending upon context, if I'm just writing code for a study, I might be much more lax about what I write than if I'm, say, writing software for a banking system, right?
Yeah, that's a very interesting question. So we didn't ask them to write secure code. We only asked them to write code. But if you ask them to write secure code, it may not represent the real-world situations, because many developers in real-world situations, they only care about the functional outcome of their code. They don't care at all about the security of their code, or they even don't care about the end users. And this is the problem that we want to tackle. So we cover simple text, or not very sophisticated, but we focus on the usability. So if you can help them, if they don't have security knowledge, still they can write secure code.
Well, yeah, but again, even if they have security knowledge, they may not put forth the effort unless they know the context demands it.
Yeah.
Right.
Yeah.
So, okay.
Yeah. Thank you.
Thank you.
Thank you.